Hi, everyone, and welcome to Electric Power Systems. My name is Behnam Askarian. You can call me Dr. Ben. Most of you are already familiar with me. You already know my office. It's in room ECS 221J. My email is baskarian@wtamu.edu. And my office number is 806-651-5248. My office hours are Monday, Wednesday, 9:30 to 11 a.m. But usually on Monday, Wednesdays after the class, I would be in my office. So if you have any questions, just please stop by my office and I will be happy to help you out. If you want to set an appointment at another time, just please email me, and usually give it like 24 hours if it's a business day, because I get a lot of emails to reply, but I will try, especially this semester, to reply to your email as soon as possible. This course doesn't have any required books or materials, but the recommended material is the books that are mentioned here. I will provide with all the necessary materials that you would need. Only thing is, for your exam, it's good to have a calculator and some engineering papers. For this course, the objective of this course is for understanding per unit systems, phasors, symmetrical components, and fault analysis, the current and voltage transformers, relays and overcurrent protection, transformer protection, and line protection, and three-phase, also single-phase, three-phase, reactive, real power. We're going to do a little bit of review on those as well. You are already familiar with the program learning outcomes and ABET accreditation requirements. About the assignments, when I post homework, you would have 7 to 10 days, usually it's a week, to submit your work. And late submissions will not be accepted unless it's pre-approved. So it will get an automatic 0. Also, for online students, I would not accept late homeworks and late quiz. If you missed the deadline on your quiz and exam, I will not give any extension on that unless someone has a family emergency or health medical emergency or something like that, and they need to have the proper documentation for that. So this semester, I've decided to put a hard deadline because I had some problems in the previous semester. Students wanted to take the exam, and I had to post the grades approaching the deadline, and I had some problems with that. So it's going to be a hard deadline for the homework and also the quiz and the exams this semester. For this class, we would have 2 exams, 2 midterms exams. Each would be 25%. We're going to have homework assignments, which are going to be 10%. And we're going to have a random quiz, which is going to be another 10%. And the final exam would be 30%. So no final project like the previous classes that you had. And the quiz would be also attendance as well, so student involvement. It's going to be random. You may have 2 in a week and none next week. Again, it's for me to keep attendance as well. The grade scale of 90 to 100% is A, 80 to 89% is B, 70 to 79% is C, 60 to 69% is D, and below 60% is F. If you get a D in this class, you have to repeat the class. So anything below C is automatic repeat. So very important about cheating policy and the use of generative AI and academic integrity. Please read these carefully. So for this course, we have a strict policy on using generative AI you cannot use generative AI in any of your assignments. Again, generative AI is not permitted in any of the assignments. So if you use it in your homeworks, exam, or quiz, it's an automatic 0. So especially for online students, I'm gonna repeat this. Using any type of generative AI on your exams, and I had problems with these in the previous semesters, is gonna be an automatic 0, okay? There are some ways that I realized that I can find out who is using ChatGPT, and using those methods, I can easily determine who's using it, and it's going to be an automatic 0. So please do not try any generative AI in your exams or in your homeworks. The exam work must be submitted for the online students, and for the in-class, you have to have your work, and that will be also graded. And also on top of that, I would actually encourage, if you want to do your homework in group, again, it must be your own work, not copying each other, but if you want to help each other out, have a discussion on your homeworks, that is encouraged, but for exams, quiz, strictly prohibited. And again, the final objective of this course is for you to learn. I know most of you would forget many of the equations that you're going to learn in this class, but if you learn these concepts, it's going to stick with you. It's going to stay with you forever. The equations would be provided for the in-person students on the exam, so I will give you like a cheat sheet with all the equations on it. And for the online students, I would give them with all the necessary equations on their exam. But other than that, no notes, or using any type of online resources or books is actually acceptable on this exam. Now, another thing, you already have these on all your syllabus, so I would recommend this to read the statements. And let's go down to the tentative calendar. In this course, we will have the following schedule. The first week, we're going to have chapter 1 and 2, which is introduction and per unit theory. Then we would start with symmetrical components, sequence networks, and symmetrical fault analysis. Unsymmetrical fault analysis, CTs and PTs if we have time, relays, overcurrent protection. Then we have the spring break, transformer protection, line protection, conservation laws, and electrodynamics and electromagnetic waves. And we're going to have finally the final exam. The syllabus may differ a little bit from this calendar. I would try to cover all of it, but we may have a little bit of deviation from this, because some parts I realized that the students didn't learn from or didn't have the prerequisites for it. So I'm going to go deep into some parts. For example, for transformers, we may spend more time on transformers and modeling transformers and so on. Do you have any questions about the syllabus? No? Okay. So let's start with the course. So again, ENG 4371, power analysis, power system analysis. Some of these materials are adopted with permission from Professor Tom Overby. He's a professor. He was a professor at Orvener-Champaign, and now he's a professor at A&M University. But I have added a lot of PowerPoint slides from myself or from the book, and I've put the sources in each slide that is, reference. So if you want to get more information on that, please go to those references. The PowerPoint that I'm sharing today may have a little difference between the one that you have here and the one that it's uploaded on the website. The reason is because I have to update all the graphs. So I had the numbers for 2023, 2024 for last year. This year, it's for 2025. So all those graphs have been updated. The numbers have been updated and so on. Another thing I forgot, I have to mention here, is that all the materials have been already uploaded, all the class and lecture notes. I've also included a podcast for the class and using Notebook LM, and I just give him the chapter of that book with additional information, gives you this podcast. Online students and also in-person students have benefited from this a lot.
Exactly. Today's deep dive is from
This is a sample of the first chapter. And one thing that I want to mention is please utilize this. You can, put them on a MP3 player on your phone and play them while you're driving. So if you don't want to go through the, materials, or you want to just remember, these podcasts would help you a lot. Each of them are about like 30 minutes. Some of them are an hour. But for each lecture note, I have put a podcast that you can use. There's also the videos from the class that I would also put on my YouTube channel, and I will put a link for the in-person and online classes here. So if you missed a class or you want to revisit a class or review a class again, you can watch the videos as well. I haven't uploaded any of the assignments yet, but from this weekend, you're going to have your first assignment. And for the online students, after every video, they're going to have a quiz, 1 or 2 question quiz, to see if they have actually watched the quiz, the videos, and the quiz is about that class. And sometimes that quiz would be just maybe something I said on that class, which is not necessarily in the notes, just to make sure that the students watch the videos. Yeah, that's it for the course material. Do you have any questions? No? So again, as mentioned, the course lecture may be a little different from the thing that I would teach now, because again, I usually update all my PowerPoints every year, add materials and so on. And I will add this, again, I will replace this with the ones that are already on your Canvas. Okay. Now, this course syllabus, we're going to have, again, introduction and review of phasors and three-phase transmission line modeling per unit, model for transformers, power flow analysis, economic systems, short circuit analysis, transient stability, system protection, and distribution systems. If we have time, the last 2 depends on how much time we have. So let's start with basics. A simple power system, every power system has 3 major components. We have the generation, which is the source of power, ideally with a specified voltage and frequency. That could be a DC, AC source. We have a load, which consumes power, ideally with a constant resistant value. And we have the transmission system, which transmits the power ideally as a perfect conductor. So we have generation, transmission, and consumption, which is load. But it's not that easy. We have complications in the system. We don't have an ideal voltage source. For example, if you have a solar farm in the morning, you would generate different voltages and powers compared to the evening and afternoon and evening. Same thing is for a gas power plant. Depending on how much the turbine is spinning and how much the temperature in the chamber is, you may have different outputs of energy, voltage, and also frequency. The next thing is that the loads are seldom constant. The transmission system has inductance, resistance, capacitance, and flow limitations. One example that I can give is when you have a transmission line, and it's like a 3-phase transmission line. If you have multiple conductors, wires, moving in parallel. The air between them acts like an insulator. And what you technically have here is you're going to have a capacitor, okay? This could be the capacitor between the neutral and one of the phases. So capacitance, we have capacitance on the line. Other thing is inductance. So you've seen that these wires are twisted wires and they have inductance. So they have inductance, capacitors, and also the wire itself. You don't have an ideal conductor. It has resistance. Mainly these transmission lines. Do you know what the transmission lines are made out of mainly? That's some of them are the twisted ones, but the thing is, mainly are aluminum because steel is heavy, a lot of resistance. So mainly they are made out of aluminum. Copper is extremely expensive. They can't make it out of copper. Copper is the best. It's gold, copper, and then aluminum. Gold and copper obviously very expensive. Gold is used in microprocessors for connections, very small quantities. Copper in motors, you use copper because still aluminum is generates a lot of resistance and heat. But a lot of these transmission lines are aluminum alloys, not just aluminum, just, they make them from aluminum alloys. That's the reason you see some of these wires being stolen, because aluminum is expensive. So they cut them and they sell them, or if they want to reuse them, they will cut them and melt them and reuse them. Yes?
I thought that the capacitance and transmission lines was between your lines and the earth.
Yes, it's between, as I mentioned, this is neutral. This is one of the phases. It could be between neutral or one of the phases, or even two of the phases because they have a different phase. There's a system what we call bundling the lines, and I'll explain about that as well, the bundling. But yes, it could be, as I mentioned, between ground and one of the phases, or is between the phase and the neutral, the phase, and if you have like a middle pole, so any of that creates some capacitance, depending on the frequency and what frequency that resonates. So you have capacitance and inductance. As you have learned from measurement and instrumentation systems, a resistance drops the real power. Okay, so if you have resistance in the system, the real power delivered is going to be decreased. Capacitance and inductance creates another problem. Do you remember what problems they caused? So yes, what was it? Yes, reactive power. And capacitance and inductance don't have any effect on the real power converted and transmitted, but they have effect on the reactive power, and they cause leading or lagging reactive power. They would actually affect the power factor. And as you know, a power factor has an effect on the total apparent power that we have. So we want to minimize these reactive powers and maximize the real power. That's the reason we have the power factor compensation at the end, which are usually capacitor banks, if you remember from measurements and instrumentation. So some notations of power. Power is instantaneous consumption of energy. Power unit is usually in watts, which is voltage times currents for a DC or watt. 1 kilowatt is 1,000 watts. 1 megawatt is 1 million watts, or 1 times 10 to the power of 6. And 1 gigawatts is 1 billion, or 1 times 10 to the power of 9 watts. The installed US generation capacity is in 2025, by the way. In 2024, it was 1,160. 2025 is 1,230 gigawatts, or about 3.4 kilowatts per person. The maximum load of Amarillo, this is from Open Data, Xcel Energy, is about 476 megawatts. This is the latest that I could find. And Dallas is a part of the ERCOT grid, just Dallas itself, not the fourth ward, and which sets new peak demand records in summer of 23, exceeding 80 gigawatts for that. Now, power is different from energy. Energy is the integration of power over time, and energy is what people really want from a power system. So it's amount of power that you use usually per hour. So energy units are joule, which is 1 watt second. And then we have kilowatt hour, which is the main one that we use. And 1 kilowatt hour is 3.6 times 10 to the power 6 joules. And another unit is BTU, and it's 1055 or 1055 joules. And 1 mega BTU is 0.292 megawatt hours. BTUs are usually used in cooling, air conditioning systems, and we show them with BTUs, like we say, like 5 ton or something like 12,000 BTU or something like that. So it's for electricity measurement, we usually use kilowatt hours. BTUs are usually used for cooling and heating, and also. So you may see a BTU even for a gas furnace. Does anyone know what BTU stands for? Yes, British Thermal Unit. And US electric energy consumption is about 3,600 billion kilowatt hours, or about 13,000 kilowatt hour per person, which means on average we each use 1.5 kilowatt power continuously. So this means 24-hour, this is an average that we are using. Now, some power system examples, we have electric utility that could range from quite small systems, such as an island, to one covering half the continent. We have 4 interconnected AC power systems in North America, which are operating at 60 hertz. Other countries, such as European Union countries, they use 50 hertz. We use 120 volts, they use 220 volts usually. This is for a utility system. For example, for spaceships, for airplanes, they would use higher frequencies around 400 hertz, because that reduces the weight. And the weight is, so you would have smaller power electronics for them. And it will be used in ships and submarines, in automobiles, which EVs are now using 300, 400, 800 architecture. So EVs, they usually started with 200 volts, early Teslas, then jumped to 300 volts. But newer cars have 400 is standard, 800 volts. I see that in a lot of cars, like the new Lucid cars as well, or Rivian. And even BYD has 1,000 volt architectures. The higher the voltage gets, the power electronic side is easier, but you need much more insulation. It's much. So a 12 volt battery is not dangerous at all. You can touch it, easily hold it, it's not going to be dangerous. But anything about 60, 70 volt DC, it's going to be extremely dangerous. By the way, DC voltage, contrary to public belief, is way more dangerous than AC. The reason is that AC, you have it's actually going from positive to negative. So it's oscillating voltage, and it passes at 0. So it's passing electrons and then going past 0. But DC, it's just constant, continuous current passing through your body. It actually destroys every single cell. So 200-300 volt DC is extremely dangerous. If you create a closed loop, it's fatal. It's gonna kill someone instantaneously. So 400, 800 volts is going to be a little more dangerous, but it has a lot of benefits. If you want, we can explain it in the class, but you're going to have a smaller motor, power electronics going to be very easier to design charging, it's going to be fast charging is going to be way easier when you have an 800-volt architecture compared to a 200-volt. The maximum fast charging that you can go with a 200-volt from 20 to 80% is going to be like 45 minutes, 1 hour. For a 1,000-volt architecture, BYD has a 1 megawatt charger now that charges 20 to 80% in 5 minutes. So going from 1 hour to 5 minutes, it's a huge jump. Yes.
How does an increase in frequency reduce size of components?
Okay, that's a great question. So did you have power electronics? Yeah, you haven't had power electronics. So in power electronics, the higher the frequency goes, you have better control over the system, and you have smaller switches. You can have more rapid switches, and it generates less heat. So you can have a smaller component, less, heat sinks. You don't need those bulky fans. It has a lot of benefits. You would definitely have a better output, very close to a sinusoid. If you want to create a pure sinusoid wave, you're going to have less harmonics. Third, fifth harmonic is going to be way less. Therefore, you're going to have less power waste, less heat generated, and so on. So you can build it smaller. Yeah, there are a lot of benefits. And so if you want, for example, a very smooth DC output, the 400-volt gives you a perfect. So the thing is, depends on the output voltage again, and it's not just about the frequency. It's about the output voltage, input voltage, how much current output that you are doing. But up to like 2-3 kilohertz, from 2 hertz to 3 kilohertz, not a problem with these transistors and these switches. Anything above a few megahertz, that's going to be difficult. But in this range, even small normal transistors and choppers, what we call the chopper DC, it's very easy for them. So 400 hertz, 50 hertz, not a difference for that switch. But if it goes above 10 kilohertz, 20 kilohertz, then it's going to be an issue. And we usually don't go above that for power electronics. Those very high frequencies are just for communication systems. We will barely go above like 2-3 kilohertz for these. And it could be done with any. Exactly, yes. And those signals, sometimes, I'll give you an example. An AM radio station, it's extremely high power. You can cook a hamburger on an antenna. It's like this power. It's very powerful. Those, you can't even use regular semiconductors. The semiconductors are in the range of maximum like few kilowatts. Sometimes those require like 100, 200 kilowatts, for example. A normal one is like 20 kilowatt power, because AM transmits from one side of the world, transmits the radio frequency, it hits the stratosphere, it's reflected, it's like a mirror, and you can get it on the other side of the world. That's the reason an AM station that is in London, you can get those. FM is around 20 miles. The curvature of Earth limits it. That's with the AM, you have to have very high power to send that signal. Now for those, because it's very high frequency and high power, they use actually vacuum lamps. Still they use vacuum lamps because those are very powerful and very reliable, but not as efficient as a semiconductor. Semiconductor technology has actually become very advanced in the recent years. Like 10 years ago, 20 years ago, you couldn't even imagine that a semiconductor could go up to a few kilowatts of power. That's the reason we have EVs nowadays. Like 20, 30 years ago, it wasn't the limitation of the battery itself, it was the limitation on the power electronic components, that we couldn't have these even the drones, the power electronics and the drones and the cars have become very cheap and very powerful and high frequency. Yeah. Do you have any questions for you? So in EVs, we have 1,000 volts, 1 kilovolt. It's nowadays has become normal in this situation. And the other one is the battery operated portable systems, and also the backup systems and battery power storage systems. This picture shows the North American interconnection. It's color-coded. Each part is shown with a different color. We have 4 main interconnections, and I've divided it actually to smaller ones, but you can see the 4 main ones. We have the ERCOT, which is Texas. And the interesting part, we live here, yes? You can see that we are not actually a part of ERCOT. So if you look at Amarillo, we are not part of ERCOT. We are in the EXO. Energy is actually part of the Eastern interconnection. So as you can see, we are in this part, which is the Eastern interconnection. Actually, we are here. I'm sorry. We are right here. And so we have ERCOT, we have Eastern interconnection, we have Western interconnection, and we have the Quebec interconnection. That's the reason Amarillo, Lubbock didn't have that blackouts in 2020, 2021. Do you remember the winter storm that happened? And there was a blackout in Houston, Dallas, Austin, San Antonio, because that was operated by ERCOT. They had problems with their generation. The gas pipes froze and they couldn't run their backup generators, and they had to have the scheduled blackouts. I had a lot of friends in Houston that they didn't have power for a week, and their pipes just bursted because it was so cold. But fortunately, Amarillo and Lubbock didn't have that problem. It has its own benefits, but it also has a lot of problems, because the benefit is you're isolated. So if this part has a problem, it doesn't transit. But again, you don't have any connection with any of these. So if you have a problem, you're going to be on your own. But the Western and Eastern, they have interconnections with each other as well. They sometimes share energy as well. There was another storm, I think 2 years ago in Houston, and it created the same problem. It knocked out a lot of these transmission lines, and Houston didn't have power in July for a week. Imagine living in Houston for a week in July. I was there actually, and I just left. It was so hot. You had to sit in your car during the day just to, yeah. So yes, please.
When it comes to each of these different connections, is it dependent on different companies that run these?
Yes. And if you want to go to into the history, in the smart grid class that I teach also, I go deep into that why even these have been, divided like this. Some of them are, local governments and politics. Some of them are these big companies, divided them like this. Yeah. Any questions for this? Okay. So this class focuses on electric power systems, but we first need to put the electric system in context of the total energy delivery system. We use electricity mainly for energy transportation, meaning sometimes it's going to be easier, cheaper, and cleaner if you heat your power with electricity instead of coal. 100 years ago, they heated the homes in winter with coal. Now in an apartment, you can burn the coal hundreds of miles from the city, so the pollution is out of the major cities, and you can move the cheap and clean energy electricity to the homes, apartments, and heat the apartments. That's the reason electricity has become very, very popular. Still, there are some disadvantages as well when you transform one type of energy to another, convert one type, for example, gas to electricity. You have about 30% efficiency. So if you get, 1 joules of heat from gas, if you convert that to electricity, you get 0.3 joules. So you'll lose like 60-70% of that. That's the reason heating. So if you have gas is going to be much cheaper and also much more efficient compared to if you want to heat your house with electricity. But sometimes gas, again, it's dangerous. You can't use it in an apartment. Most of these apartments, you have to have electricity codes and so on. So electricity is a cheap and safe, easy way to do it. About 40% of US energy is transported in electric form, and the rest is oil and gas, mainly because industries, a lot of those industries, they burn coal or gas or oil, and you have oil and gas and diesel used for transportation as well, which is a big part of the energy consumption of the US. I actually added a slide. That's a very good question that you asked. I've added a slide that shows how much energy consumptions because of these cloud services. Yes, it's like going up 3 times, and everyone's electricity bill is going to go up. It's going to be bad for consumers, but it's very good news for electrical engineers because it's going to be a lot of job opportunity for us. So they can't keep up with the demand right now. Literally, the GPUs, NVIDIA GPUs are melting down right now. So all these, clouds and AI centers, they are working at 100% capacity. And I have a clip if you want, I could show you. In the dot-com bubble, they laid down all these fiber optics, and they only lose that 8% of that. Now the data centers that we have, we are using 100%, so it can't keep up. And imagine in 10 years, if they want to replace a lot of jobs, they would need way more data centers. Without the data centers, the power consumption is going up for everyone around the world. And I will show you different options that we have. Definitely, we have to bring back nuclear is one option. Renewable can help as well. And they're thinking, I don't know if you heard, like Facebook and Microsoft have deals to reopen the 3 Mile Island nuclear facility. So they are, reopening the nuclear facilities and building new ones. A new technology is the SMR. I don't know if you heard, the small modular reactors. They are the size of this room, but they are mass produced. And so basically, it's like having the nuclear reactor, which is in a submarine right now, and using that as a power source. So they would mass produce it, and they would put in these container ships, and you would just install it in a city like Amarillo. They're from 1 megawatts up to 300 megawatts. And because they're modular, you could put like 10 of them together. Yes, it produces more output. They have a passive cooling system, so they don't have any environmental concerns that older ones have. You charge them once, it works for like 10 years, then you bury the whole system. It looks like that. And because they have a passive cooling system, it's much safer and smaller. And some of them, new generation, are using molten salt, what they call. If you want, I can give you it's a whole class about SMRs. It's a growing, and I think in the next few years, we're going to have the first ones coming out. The problem right now is the economy. They have to make it, so until it's mass produced, the price is higher than, normal nuclear. One of the cheapest forms of electricity generation is actually nuclear. The upfront cost is huge, but in 40, 50 years, it offsets. Some nuclear plants could actually last for even 70, 80 years. Some of them are right now working in Armenia or Ukraine are 70, 80 years, or they're from the 60s and 50s. Yes, there's a lot of bureaucracy and red tapes that you have to. One example I can give you: UK is building the largest nuclear power plant in Europe. They thought it would cost them like 12 billion. Now it's like 30 something billion, and they are like 5 years behind schedule because they have to change the design and I'll give you if you are interested, I will show you a very interesting video on how much actually nuclear energy is one of the safest forms of energy. There's been a public, but it's one of the safest. In total, maybe 20 people have died out of these nuclear the safest form is actually solar, wind, and nuclear, these three. And next one is going to be hydropower that kills like 300 people a year. So it's very safe form of energy.
That would be, everybody's afraid of.
Yes. It was because of the early 70s and 80s, the Chernobyl and the Fukushima disasters. So concerns about need to reduce CO2 emissions and fossil fuel depletion are becoming main drivers for changes in world energy infrastructure. This, I've included two graphs. This is the 2015 energy pie, where we had around 2% of energy from wind and 0.6% from solar. Now, how much do you think the electricity generation has increased in the 10 years? This is, by the way, the whole energy. And I have the newest data. In 2025, wind accounted for more than 11. It was 11.2% of total electricity production in the US. In New Jersey right now, they have so many proposed wind and solar projects that it takes 30 years to approve all of them. So they have a huge backlog in a lot of states. The problem isn't the power production. It's become very cheap right now. The problem is the grid. So the grid has a limited capacity. The grid is aging. So the transmission, the companies like ERCOT, they are regulating how much generation could come in. And that's the problem that we have. And that needs huge investments to improve the grid. Solar was about 7%, and it was mainly solar panels. There were only a few thermal panels. One was in Nevada, California, Nevada. I don't know if you drove between LA to Vegas. You can see those big ones. It's like right across the highway. And they shut that down because it didn't make any sense. Because solar panels have become like extremely cheap right now that they are competing with those. Geothermal was 0.4 and hydroelectric was 8%. And you can see solar is reaching hydroelectric and wind past that. And this is the historical energy usage. And you can see that renewable energy, and actually in 2023, 2022, renewables accounted for 22% of US electricity generation, surpassing coal for the first time in 2022. This is the renewable energy consumption. You can see the hydro stayed flat. Wind and solar have skyrocketed. And the reason is obviously we have limited amount of rivers and places that we can build these hydroelectric dams. And this is the growth in the US wind power capacity. And the development time actually is pretty short right now. They make it in these factories. They have the only part is getting the required, as you mentioned, approvals for installation and so on, transportation and installation. That part is the time-consuming part. The production itself, it's actually very streamlined and easy right now. This is the wind capacity installation by states. And as you can see, we have this, what we call the wind corridor. It's around here. And the majority of the wind, it's actually a little bit like this, is produced in this area. And Amarillo is in what we call category 3 winds, is one of the best places in the world, the Panhandle area, to generate wind power. Obviously on the east side and west coast, we have offshores. California has a lot of offshores as well. But the best place actually is in Midwest to generate. And you can see that Texas is leading by far in wind energy production. And one good opportunity for those who are looking for a job is, and we provided that previously, is for you to get a wind technician certificate. Texas Tech also provides that. And the salary is very good. If you become a designer or technician, it's like $130, $140. And it's not a very difficult job for maintaining those wind turbines. And This is the illustration of the wind turbines and their concentrations, and different heights of the wind turbines. And you can see the majority of it is in this. Just looking at the map, you can see where it is concentrated. The major problem is not generation, is transmission. So we generate all of these power. We can technically generate the whole energy need for the US and Midwest, but the majority of the populations are in the coasts, 85%. And moving that, for example, from here to Los Angeles or Florida, it's a 2,000-mile journey with a lot of waste, a huge infrastructure, a lot of costs. One thing that they are doing, these cloud companies, you see a lot of these data centers and cloud systems popping out here because they want to use this cheap renewable energy. Now, these are the world energy consumptions by energy source from 1990 to 2040. And you can see that natural gas and renewable is increasing and coal is decreasing from the total share. And overall, the consumption is going up. So a little bit about energy economics. Electrical generation technologies involve a trade-off between fixed cost or cost to build them and the operating costs. Nuclear and solar, high fixed costs, but low operation costs, though cost of solar has decreased substantially recently. Natural gas, they have a lower, what we call the CapEx or capital investment, and a higher OpEx. Why? Or operational. Natural gas, you need the fuel. Fuel is expensive. So at front, it's lower investment, but during the whole lifetime, it's going to be more expensive. And coal, wind, hydro are in between. Again, why wind, solar, renewable energies, you don't need any fuel for them. So the OpEx and maintenance is going to be much less. Also, the units capacity factor is important to in determining the ultimate cost of electricity. This is an example. This is an old figure from 2012, and I will show you the newer figure from 2025. And you can see this is a comparison between conventional coal, advanced coal, and natural gas, and nuclear, and wind, and solar. You can see in 2012, nuclear was somewhat between, but natural gas was the lowest. Solar and wind were the highest in 2012, 13 years ago. And these energy costs depend upon the capacity factor. For the generation, the capacity factor is the ratio of the electricity actually produced divided by its maximum potential output. So for solar, we know that it doesn't work at night. So that cost is divided between like the 8 hours. So if you pay $1,000 for a solar panel, you can only use it for 8 hours. But if you pay $1,000 for a coal power plant, you can use it 24 hours. Okay, so this is the unit price dividing that. Nuclear power plants almost never shut off unless they have maintenance. That's the reason 24 hours, 24/7 nuclear power plant is creating the baselines. Solar, wind, hydro, they are usually fluctuating, and hydropower is usually used at the peak demand. And this is the natural gas price. You can see when it's just fluctuating. So if you want to, nowadays, if you want to put a large CapEx and build these natural power plants, and there's another war in Ukraine with Russia, naturally gas prices jump. So there's an uncertainty about that. But for wind and solar, you don't need to worry about the cost for the fuel and so on. And the same thing has happened for coal as well. You can see that the ranges change, and there's a lot of environmental impacts. Actually, a lot of companies now, in some companies, you have to buy what we call carbon credits, and they do it actually in the US. A majority of the net income for Tesla comes from these carbon trades. So what it does is when GM sells an internal combustion engine car, like a Chevy Silverado, they have to buy carbon credits from Tesla because Tesla's building an EV. So they actually pay Tesla to buy those carbon credits. It's like free money. If Tesla didn't have that last year, they would actually lose money. And they lost money this year because they got rid of that in the new bill. So that carbon credit is now gone. But prior to that, for the last 15, 20 years, I think 15 years or so, there was what we call a carbon credit. Some companies, you have to pay them, and they use that carbon credit to capture CO2 and then inject it to the ground. So it's a business, actually. They call it carbon sequestration or something like that. Carbon capture technology is getting huge. Now, this is a nice example of solar power prices between 75 and 2023. In 75, it was $100 per watt. So 1,000 watt, 500 watts panel that is $120 now was $50,000 in 1975. So it went from $50,000 down to $150. And this shows a graph from 2009 to 2017. It's going still down. It's way lower than this now. And you can see a sudden decrease when it was mass produced and started mass production in China. You can see that the solar and wind has dropped significantly, and nuclear, coal, and gas, all of them have stayed steady or even increased a little bit. So we saw this, and you saw that in 2012, these two had one of the highest energy costs per unit. And now this is from 2024. What has the lowest? Solar and wind. So the page has flipped in a decade. Now solar and wind have become the cheapest forms of energy on their own. This is a range, and you can see for lifetime extension, with subsidies, wind becomes almost zero. It becomes like almost free if there's government subsidies. Without subsidies, you can see that minimum without subsidies, and this is the range minimum to maximum. You can see it's the cheapest form of energy. Also, solar is right after that, and then it's gas, combined cycle. Combined cycle means that some generators, like the Exo generator in the Northtown, they actually use coal, but they are actually transferring that to a gas power plant. They are retooling it for gas power plant. The way that they work, it's like basically having a jet engine, for example, some of them, and you put gas in it. That one doesn't work like that. That has a boiler, it boils water, and the water goes through a turbine, generates an electricity. Other type, which is more efficient, they have like a jet engine. They inject gas with high pressure air. It spins a jet turbine. It produces electricity. Then the hot air from the exhaust goes into another system to heat up water, and that water is then evaporated again, put through a turbine, and generates electricity. So it has a dual stage, what we call a combined natural gas. Those are the highest, efficiency systems. These ones are a little older. And those have the price a little bit higher, between 45 and 108. Then we have onshore wind plus storage, and you can see that is a little bit more expensive. Still 45, but the higher end is 133. And do you know what the price increase comes from onshore wind plus storage? The battery storage systems and the inverters. Okay, so yes, it could be directly. So we have these systems that we converted to DC, AC to DC, and we also have these asynchronous generators, and some of them are even DC generators, but I'm not going to go into that. Most of them are AC. We convert them to DC. Some of them even have the power bank right at the bottom of the tower, and it gives you that to the power bank, and they will use it in the peak hours. And the extra cost is for the batteries. But the price of battery is coming down as well. It's becoming substantially cheaper. Now, CATL has came up recently, 2-3 months ago, with a sodium battery. So sodium battery, as you know, sodium is much more abundant than lithium, and the cost is 1/3. It has other advantages. It never blows up. It's very safe. It's basically salt water or something like that. And you can, so lithium battery, when you send it, it has a little bit of charge in it, makes it a little dangerous. That's the reason when you want to return something in Amazon that has a lithium battery, it requires you to print that certain, tag put on it that this has battery and it's dangerous. A sodium battery, you can send it depleted. So just have the mixture, send it, and they will charge it. So it's extremely safe, very cheap. For the stationary, they are heavier, less power dense than lithium. But in other words, when you have a stationary system, it's not a car. They are putting it in cars as well. The new, I think, Chery and BYD are using that as well. But you have a lot of space. You don't care about weight. Sodium batteries, or we have liquid batteries, other type, and also solid state batteries are becoming cheaper. I think in the next 10 years, it's going to be this graph would move to the left, and it will become very, very much cheaper than gas. At that point, it would not make sense to build any gas power plants or coal power plants. So right now, as you can see, it's much cheaper with storage than coal. That's the reason there's a lot of interest in having these renewables with battery storage system. And it's a good business. I have a friend that works in Houston. He bought 20 acres around a transmission site. So if you find a power transmission site that has free land around it, they go and buy it. Okay, if you tell them, and they will give you like a referral money as well. If you find something, and they will give you, oh, you found this for us, they'll give you $1,000. And right now they're building 3 different sites. So what they do, they just put these large energy storage systems. They don't have any generation at all. They will buy the power from the grid after 12 a.m. and they charge the battery and they sell it back to the same company during the peak hour. So they find the transmission, station, build it right next to it, add batteries, and one thing that they are working and they asked for my help was that now they are buying these old EVs, very interesting. These old Nissan Leafs and Teslas, when they reach the end of their life, they are sold for $2,000-3,000, for example. But the battery is it has 80% life left in it. So they take out the batteries, sell the rest of the car for scrap. The battery becomes like $1,000-2,000, and they have built these software and hardware systems. They put in the containers and they reuse it for the next 10-20 years. So this is a nice business model that they're using and making a lot of money. As I mentioned, they're buying a lot of land and doing this. So without generation, you can still make money out of it. And you can see solar plus storage is a little bit more expensive than wind. And then we have geothermal and coal, and finally offshore wind. Offshore wind is more expensive. But the good thing about offshore wind is it doesn't require a lot of storage. Offshore wind is more consistent and predictable than onshore. Usually it works like a majority of the year offshore wind is there. Now, going back to your question, that was a very good question. This graph shows the data center energy consumption surges and the AI boom. You can see 20 to 35. Coal, natural gas, nuclear, renewable energy. And this is on the left, you can see the global demand, China's demand, and US demand. And you can see the projection is by 2035, all these power generation that we developed in the past 100 years, we need almost double that. So the same amount that we have 1,000 gigawatts, we need to build at least another 1,000. So we have to double everything that we did in the past 100 years, more than 100 years, we have to do it in a decade. It's a huge load, okay? So, and we have an old infrastructure, transmissions lines, all of that must be updated. You can't just go and build these generators and connect it to the grid. You have to upgrade the grid, the system, so it's going to be a huge challenge. And you can see globally, it's going to be almost 3 times the size. Why? These developing countries, third world countries, they are expanding very, very fast, and the power consumption is exploding in those as well. So you can see how, by the way, 30% of all the CO2 emission in the world comes from China, and it comes from burning coal. So all the cars in the US doesn't make any, even like 3-4% of it. And you can see the majority of the electricity that they produce is coming from coal. And they're trying to expand that and pivot toward renewable energy. Okay, I think it's enough up to here. Let's have a small quiz. For the online students, I would post a different quiz. And for you, I just want for attendance. And we're going to have a short Kahoot quiz. Thank you so much, and I will see you next week.